All right, your test is going to have both a calculator and a non-calculator portion. The test is Wednesday. Yes, so we will review today and tomorrow.
I really don't believe it.
On the non-calculator, you're going to get 3 multiple choice and a free response. Oops, non-calculator, I wrote it in the wrong spot there. On the non-calculator, 3 multiple choice, 1 free response. On the other one, you're going to get 2 multiple choice and a free response.
I love multiple choice. Cool. 5 multiple choices. Okay.
5 multiple choice, 2 free response.
Oh, that kills me.
I see. My buffer is gone.
Takes away some guessing options. You gotta actually know what you're doing on the free response.
You could get all the points for multiple choice, and then not barely get any other free response, and you'll get like a 5 out of however much it's out of, and then before the curve.
5 out of 23.
Oh my god.
So that's a 22%, which is a 60.
Oh.
So if you get all the multiple choice right and 0 on the free response, you'll get a 60.
Well, if we get like 2 multiple choice right,
That's horrible.
You will get somewhere in the 50s. So
Just planning out the grade already.
topics of chapter 10
what's the point of it?
to make sure that you're not just guessing on every question.
I think they should
What's
just
the
not
point
worry
of
about that,
multiple
because if
choice
someone's
if you're
guessing
only
and getting them all right, then kudos to them.
They don't know calculus though. So this is a problem if they're going into
But they know
engineering and
guessing.
they would take then calc 3 and know nothing. That would be a problem.
That's my problem.
Well, yeah.
But
That
why
would be
are
a
there multiple
problem.
choice then if they're only worth 1 point? It's like, okay.
So parametrics. Parametrics we learned was our first big topic. Parametrics, make sure that you can take a derivative of parametrics. When we take a derivative of parametrics, we take the derivative of each of them. Okay, our x derivative and our y derivative, and then we divide y divided by x. The y derivative divided by the x derivative. If you need a second derivative for parametrics, you take each of the individual derivatives, take a second derivative, and divide it by the original x derivative. And we'll do an example. But just kind of get topics out here. We need derivatives. You need to know the position, velocity, acceleration relationship that we've been working with all year. That those are derivatives as we move through. You need to know vectors. Mainly to understand speed, because vectors are really just parametrics. When you're given a vector, inside of a vector is an x component and a y component, so really you're just given a parametric. So if you need a derivative of a vector, just take a derivative of a parametric. That's really what you're doing there. Just take their separate derivatives. But speed is different than just making velocity positive. What is the speed of a vector? The absolute value, but that's not just making it positive.
It's the length.
It's the length or the magnitude, which we find by magnitude.
By the Pythagorean theorem.
Pythagorean theorem.
Pythagorean theorem.
Okay. So that's our arc length again.
Oh, there it is.
Except we're not integrating it. We're just doing one length instead of adding lengths. So vectors, the main thing we need to know about vectors is speed, because otherwise we can just think of vectors as being parametrics.
Are those
Then-
primes in there?
Yes.
So you derivative the
You need the velocities. So assuming that x and y are the
Okay.
position, you need the velocities.
so the speed is the magnitude of the
The velocity.
it's not of the position.
Right.
Okay.
Speed is a hypotenuse of a vector.
Of a velocity vector.
You just made that way more complicated. Why did you do that?
The third topic of chapter 6 was polars. For polars, you need to know area. We talked about that today. You need to be able to take a derivative, which we do as x equals and y equals equations. We turn them into parametrics. If you need a derivative of a polar, turn them into parametrics, and then take a derivative. So really, this whole chapter is just about parametrics, except for polar area. Everything else boils down to parametrics. Okay? Which makes it a little bit less intimidating, because instead of 3 topics, this is really just all one topic, except for polar area.
How do you turn polar into parametric again?
X is equal to r cosine theta.
Oh, that, okay.
X is equal to that.
How, doesn't that become just a standard XY function?
Only if you start combining them.
What's y?
Otherwise, it'll become an x equals and a y equals
Wait, was it
Okay.
x squared plus y squared equals
r squared.
r squared?
All right, so let's think about some examples. So parametrics, let's say x is equal to 1 plus 2t squared, and y is equal to the cosine of t. If I want to find a derivative, dy dx, then we need to find the y derivative and divide that by the x derivative. Okay, so the derivative of parametric, take the derivative of each of them, and then dy dx is just the y derivative divided by the x derivative. If you need a second derivative,
Isn't that 14 cubed?
I'm taking a derivative non-integrating. If I need a second derivative, I want to take the derivative of my derivative, that's what a second derivative is, and here we need a quotient rule. So low d high minus high d low over low low. And since we just took that derivative in terms of t, but really this is asking us to take a second derivative in terms of x because it's dx squared, then we need to divide this by the original x derivative. The easiest way to divide by that is to multiply by the reciprocal of it. And so then on the top, with some cleaning, I get negative 4t cosine of t plus 4 sine of t over 16 times 4, 64 t cubed.
I'm guessing you could factor out 4.
You could factor out the 4 and cancel the 4 out of everything. If it was multiple choice, that might happen.
You really want to be ambitious.
This
So why did
is
you
a plus
multiply
there
by-
in the middle. It kind of looks like a T. It's a plus.
Yeah.
Why did you divide by the 14 again?
Because we want to take our second derivative in terms of x. So since it's dx squared, we need to be taking our derivative in terms of x. But when we took our derivative, we actually took it in terms of t. So to cancel out that we were kind of working with the wrong variable in the problem, we need to divide by the x derivative.
Meaning the 14 on top, or?
Meaning the very top x derivative. We need to divide by that.
Oh, that's just
That's-
always the rule?
That's what goes here.
And that you always do that when you take
Yes.
a second derivative?
For parametrics.
So from dy dx to the second derivative, you take the derivative of the dy dx
Yeah.
with the quotient rule,
Yes.
and then you divide by the dx.
Yes.
Okay.
Alright, so to recap, to take a second derivative, you take the derivative of the first derivative and then divide that by the derivative of the x function from the very beginning of the problem. Okay? Typically, when you take that second derivative, you're going to need a quotient rule. Unless things canceled out nicely in your dy dx, typically you're going to need a quotient rule there. Careful with quotient rules. When students learn L'Hopital's rule, they start doing L'Hopital's rule when they really want to be doing a quotient rule. Okay? L'Hopital's rule is only appropriate if the question is asking us to take a limit, not to take a derivative. L'Hopital's rule does not take derivatives, it takes limits. Okay, so we need a quotient rule here. All right, so kind of going through that checklist, we said parametrics, we need to be able to take derivatives. That would be first and second derivatives. You need to know the position, velocity, acceleration relationship. Okay, so if you're given parametrics that describe a position, knowing that then if it asks you about the velocity, it's asking you about the derivatives of them. Okay, so you'd want to take the derivatives of those, or acceleration would be the second derivative. Now in terms of a vector is really just a parametric equation put together in brackets. So this could be a vector as 1 plus 2t squared and cosine t. And now it's a vector. Okay? So anything you're asked to do with a vector, you can really just deal with parametrics. So if you're asked to take the derivative of this vector, just take the derivative of the two pieces. Okay? If you are asked to find the speed at a certain time. So let's say I want to know the speed at time equals 3. Speed is the absolute value of velocity, but absolute value does not mean just make things positive. For a vector, absolute value is its magnitude, because really what absolute value means is distance from 0. So on a number line, we can just make numbers positive. But a vector that has an angle attached to it, that then needs a different formula. And we said that for that, we're going to do our Pythagorean theorem. Speed is the absolute value or magnitude of velocity. So we're going to plug into this the velocity function with 3 plugged in, squared, plus negative sine of 3 squared.
And then that would be your answer.
And then that would be the speed at time 3. Okay? Speed is not just make velocity positive. Speed is find the magnitude of velocity, which comes from the Pythagorean theorem. Okay? All right, we'll leave it here for today. We still have polars to review, but we'll review polars tomorrow. And then we'll take our test on Wednesday.